In section 7.4, we saw how to do recurrence relations which are homogeneous in nature, linear homogeneous recurrence relations. Now we are going to look at non-homogeneous recurrence relations. Non-homogeneous recurrence relations. CURR, recurrence relations. Okay, so just a reminder, what does it mean by a recurrence relation to be non-homogeneous? Suppose I have a sequence. Suppose there is a sequence hn, n is equal to 0 to infinity, satisfies a recurrence relation CURR recurrence relation or relation which is of the form hn is equal to a times hn minus 1 plus b times hn minus 2 plus c, right? I mean, you can have more terms, n minus 3, n minus 4, whatever, all the way, but something of this form with a b constant independent of n, and c might depend on n. C is non-zero, might depend on n. Then such a thing is called a non-homogeneous recurrence relation. Okay, so this is my problem child, and depending on the nature of C, we might be able to solve the problem or we might not be able to solve the problem. So we can't do solve all of these in general, but we can do it in some special cases, right? So I am going to tell you which cases we can do and how to do it. Okay, so example one, suppose I have my recurrence relation fix a in R. Suppose I have h of n is equal to a times h of n minus 1 plus some constant c. Okay, I don't know what this is. C is a constant. Find hn, right? Then the solution in this case, it is relatively easier. Hn is equal to, well, a times hn minus 1 plus c, which is equal to a times hn minus 2 plus c, which is equal to a squared hn minus 2 plus ac plus c, which is equal to a squared hn minus 3 a squared times a times hn minus 3 plus c plus c times 1 plus a, right? Well, this is equal to a cube hn minus 3 plus c times a squared, which I'm going to pull out into the c part, which becomes c times 1 plus a squared. And if you see the pattern, this is going to continue as a to the n h of n minus n, which is 0. So maybe I should just write h of a to the n h of 0 plus c times 1 plus a squared plus dot 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 all the way up to a to the n minus 1, which is equal to a to the n h of 0 plus c times a to the n minus 1 over a minus 1, right? As long as my a is not equal to 1. If a not equal to 1, otherwise it's just n, right? And that is my solution. is equal to, well, let me do this, is equal to this, is if a not equal to 1 is equal to a to the n h of 0 plus, well, in that case, h of 0 plus c times n if a is equal to 1, right? And that's my final solution for that problem. So this case is pretty simple. Let us do a slightly more complicated example. Example of hn is equal to 4hn minus 1 minus 4hn minus 2 plus 2, right? And I have n greater than or equal to 2, and my base case are subject to h of 0 is equal to 3, h of 1 is equal to 6. Solve for hn, right? And so the idea is you split it into two parts. You split it into the homogeneous part, which is this part, right? That's your homogeneous part. And you solve for a particular solution of the non-homogeneous part, right? The non-homogeneous part is the complete thing, but just one solution of it is good enough for you, okay? So here's how we are going to do it. So for the homogeneous part, which is homogeneous GENOUS part, GENEOUS homogeneous part, I have h of n is equal to 4h of n minus 1 minus 4h of n minus 2, and we have seen in the previous section how to solve this. Therefore the characteristic polynomial associated to it is going to be q squared minus 4q plus 4 is equal to 0. Therefore q is equal to, well, therefore q minus 2 squared is equal to 0. Therefore q is equal to 2 comma 2, and my general solution is equal to an plus b times 2 to the n. So there are two parts to such a non-homogeneous problem: the general solution and the particular solution. We have just found the general solution, which is the solution of the homogeneous part, right? Now we want a special solution, a particular solution, okay? Particular solution, okay? My formula is of the form something something, my c is equal to 2, okay, right? In my original formula, if I compare it to what I had originally, a hn minus 1 plus b hn minus 2 plus c, then c is equal to 2. It's a constant, right? In that case, I solve for particular solution of the form just some constant d, form constant, oh, let me just say d, okay? So what am I going to look for? I am going to say, hey, d is equal to 4 times d minus 4 times d plus 2, and therefore I get that d is equal to 2. I am going to put okay, so maybe I should have said here hn is equal to d, okay? So in that case I get this, right? And therefore my total solution, therefore entire solution entire solution is equal to general solution plus particular solution is equal to an plus b times 2 to the n plus 2. Now I need it to satisfy the constraints. Should satisfy h of 0 is equal to 3, h of 1 is equal to 6. Therefore, if I put n is equal to 0, I get b times 1 plus 2. Well, therefore, h of 0 is equal to b times 1 plus 2 is equal to 3. Therefore, b is equal to 1. And I get h of 1 is equal to a times 1 plus b times 2 plus 2 is equal to 6. Therefore, 2a plus b plus 2 is equal to 6. Therefore, a plus b is equal to 4. My divided by 2 is 2. I know b is equal to 1. Therefore, a is equal to 1. Therefore, a is equal to 1. And therefore, solution is hn is equal to n plus 1, 2 to the n plus 2. Okay, so this is the method you want to use if your c is a constant. Okay, if c well, maybe I should have used a different color. If c is a constant. Okay, what do we do if my c is not a constant? Let's do an example of that. Okay, example, solve the recurrence relation. Solve the recurrence relation. You see, recurrence relation h of n is equal to 6 h of n minus 1 minus 9 h of n minus 2 plus 2n, right? So this time my c is not a constant, it is 2n, right? So let us first solve for the general solution. General solution h of n is equal to 6 h of n minus 1 minus 9 h of n minus 2. Therefore, q squared minus 6q plus 9 is equal to 0. Therefore, q minus 3 squared is equal to 0. And therefore, q is equal to 3 comma 3. Therefore, general solution is of the form an plus b 3 to the power n, right? We have seen this in section 7.4. Particular solution. Now this time my c is of the form 2n, right? C is equal to 2n. Therefore, what I would have to try is something of the form, therefore, try, what did I say last time? Try particular solution, of the form form, I don't want to say Cn plus D, Dn plus E, Dn plus E. Okay, so basically if this is a polynomial, okay, same degree polynomial, okay, 2n is a degree 1 polynomial. It's not, sure, you don't have 2n plus 2 or something, but it is a n degree 1 degree polynomial, so you look for solutions of the form degree 1 polynomial. Even if it was like 2n plus 3, you would be trying for solutions of the form dn plus e. Okay, so what do I get? I put dn plus e for hn, well, is equal to hn. Okay, so hn is equal to dn plus e is equal to 6 times hn minus 1, which is dn minus 1 plus e now, because now it matters what my, if I'm taking the hn or hn minus 1 minus 9 d times n minus 2 plus e plus 2n. Okay, which is equal to 6 times 6dn plus minus 9dn, so negative 3dn plus 2n, so negative 3n, negative 3d plus 2n plus 6e plus how many? 6e, oh, sorry, 6d minus 6d plus 18d, so 6 plus 18 is 12, so plus 12d plus 6 minus 9, so minus 3e. Yeah, that's it, right? And this should be equal to dn plus e. And therefore you get, therefore d is equal to negative 3d plus 2, and e is equal to 12d minus 3e, right? Therefore 4d is equal to 2, therefore d is equal to 1/2, and 4e is equal to 12d, therefore e is equal to 3d, therefore e is equal to 3/2. Okay, so therefore my particular solution looks like, entire solution looks like, entire solution is equal to an plus b 3 to the n plus 1/2 n plus 3/2. Okay, subject to, I still have to solve for h of 0 and h of 1. Solving h of 0 is equal to, what are the conditions? H of 0 is equal to 1, h of 1 is equal to 0. Did I mention these? I forgot to mention these, I think. Right. With h of 1 is equal to 0, h of 0 is equal to 1. Okay, so you plug in at n is equal to 0, you get b plus 3/2 should be 1, so b is negative 1/2. H of 0 is equal to 1, therefore b plus 3/2 is equal to 1, therefore b is equal to negative 1/2. H of 1 is equal to 0, therefore a plus a minus 1 over 2 times 3 plus 1 over 2 plus 3 over 2 is equal to 0. And therefore, I get, solving for all of this, I get a is equal to negative 1 over 6. Okay,